Uh, can you hear me? Right. Okay. Um, in the name of Allah, hello everyone. Today I'm going to present my work with my supervisor Jack Hale, Gwendolina Palmirota, and Tony Vandam about using random circular model to simulate stochastic anisotropic flow in aquifer system. So the water flow in many aquifers is driven by a strong anisotropy. And this anisotropy created by flow features like flexures and faults. Our overall goal is to simulate INSAR surface displacement into an aquifer model to estimate aquifer properties. On the right hand, you can see the geometry of SAR satellite. So this satellite sends down a radar wave to the Earth and then receive back the surface of Earth's reflection. And then we can use this data to measure surface displacement to millimeter. And then we can use this data as input for our inverse problem and estimate anisotropic hydraulic conductivity. In this work, we developed a flexible stochastic model of the anisotropic hydraulic conductivity tensor that respects its underlying symmetry and positive definiteness. So here you can see the result of surface displacement using INSAR of Nevada aquifer pumping test. The red line shows the pumping well, and the groundwater was pumped out for 60 days. And here you can see about 50 millimeter of subsidence, and the elliptical shape of subsidence can be an evidence of anisotropic hydraulic conductivity of underlying aquifer. So we use prolastic theory to model the aquifer system. On the left hand, you can see the final element model. Here we have 3 layers with different properties. And here you can see the location of pumping well. And in these directions show the principal direction of hydraulic conductivity. On the right hand, you can see the results of our model. So it shows the deformation of the aquifer system. The pumping happened to this pumping well, and because we have strong anisotropy in this direction, we have the deformation in this direction. So we have our final element model, and here we have a hydraulic conductivity tensor as input, and then would have the deformation as output. The hydraulic conductivity tensor is like this, and we have 4 elements. But we cannot just use random values for these elements because the principal directions are perpendicular. And because of the nature of hydraulic conductivity, we use random physical symmetry and positive definiteness matrix. So we apply a spectral decomposition so we can separate scaling and rotation using eigenvectors and eigenvalues. And also we use exponential map, so we ensure the positive definiteness. In the first step, we are going to have a hydraulic conductivity tensor with random orientation and fixed scaling. On the right hand, you can see ellipsis that its magnitude, its radius shows the magnitude of hydraulic conductivity, and its direction shows the direction of hydraulic conductivity. As you can see here, we have a fixed size for ellipses, but we have rotation for the ellipses. So here we have rotation matrix, and the eigenvalues would be fixed. And remember here, R shows randomness in rotation. And then in order to arrive at a vector space setting, we would define W. And for W, we have phi, that is rotation angle. And it is circular random variable. Here you can see the histogram of random rotation angles that we generated. And I will explain next slide how we generate them. So Lark and his friends in 2014 used the mixture of 2-1 misses for a structural geological data that contains direction. So we also use it as prior model. So we would have 2-1 misses model and one way. And then we would have a mixture of 2-1 misses for prior model. And then we use the Nuts algorithm in the MCMC method to estimate the posterior. And on the right hand, you can see the Rose diagram that we use as likelihood data. So this diagram shows the histogram of fracture direction. And here you can see that we have a biomodel in the data. So then we are going to compare some models. And here we have simple 1 misses model. Oh, sorry. And mixture of 2-1 misses model and mixture of 3-1 misses model. And the green bars shows the observed data, and the blue bars shows the posterior. So here in the table, you can see the result of live-on-out cross-validation. And the result for 2-1 misses and 3-1 misses model is too close together. But because the 2-1 misses is a simpler model or have less parameter, so we chose 2-1 misses model for our data. So finally, if we want to have hydraulic conductivity tensor with random orientation and scaling, here you can see the ellipses have different sizes and also different directions. In the first step, if we have just randomness in scaling, so the eigenvector would be fixed and the eigenvalues would be random. And then you remember we had R as a rotation matrix. So because we consider these two approach independent, so we can combine them. So then the hydraulic conductivity tensor with random orientation and scaling would be this equation. So finally, we have thousands of random hydraulic conductivity tensor. And we need to run them through our proelastic final element model in HPC. And then we would have thousands of outputs. And then we need to do some statistical analysis. We are not yet done with the analysis. But here, I'm going to show you the mean of surface displacement of random AHC, and in compare with the surface displacement with fixed AHC in X direction. Here you can see we have an effect of the random AHC tensors. So generally, we are trying to understand better the aquifer system and estimate aquifer properties. And to this matter, we are using INSAR technique instead of digging wells, and it makes this process easier and cheaper. So we build an proelastic final element model to simulate the aquifer system with AHC. And then we develop a flexible stochastic model of the AHC tensor that I'll explain today. And the next step would be to solve the inverse problem using INSAR data and estimate the AHC. Thank you for listening. I would like to thank my colleague Damien for modeling selection, helping me for modeling selection. And also, if you're interested in my research, you can contact me in my email or you can ask me questions here.